So welcome back. This is lecture 34 in this course on Bayesian modeling, and the topic for this lecture is some examples where we recover the posterior using Markov chain Monte Carlo. So we will do some examples where we implement Markov chain Monte Carlo sampler. Okay. So I think one example that we already discussed is using a binomial beta distribution, right? Now we are going to discuss an example where, let's say, you are interested in modeling number of road accidents that occur in a day in a city. Okay, so you are interested in modeling number of road accidents in a day that occur in a particular city. Okay, so this is the data you want to model, and let's say these are your likelihood and prior assumption. So let's say xi is the number of road accident on ith day, and you assume that it comes from a Poisson distribution with underlying rate parameter lambda, and on lambda, let's say you set up a gamma prior. Okay, you set up gamma prior on lambda with let's say with underlying parameters, underlying shape parameters 10, 10. Okay, so this is your setup. So this is your likelihood assumption, this is your prior assumption. So this is your model. Okay. Now our goal is to calculate the posterior distribution of lambda given some data. So let's say data you observe from 5 days. So these are the data, number of road accidents recorded on previous 5 days from Kanpur, and the data shows you that the road accidents on previous 5 days were respectively 8, 12, 14, 7 and 9. Okay, so these were the recorded road accidents on previous 5 days. Okay. Now using this data and given your likelihood and prior assumptions, your goal is to infer the posterior distribution of lambda given this data. Okay, so which would be given by likelihood given the data, prior distribution of lambda divided by marginal likelihood. Okay. So we can analytically derive the posterior here because you have a conjugate prior. So gamma prior is a conjugate prior for a Poisson likelihood, and we can also estimate the likelihood using we can also estimate the posterior distribution using MCMC, and we will compare whether we are doing fine or not. Okay. So I will now go to R code. So basically we will implement the same MCMC algorithm for this particular example. So what we are interested in modeling, so not this example, so let me just open, yes, so this was the example that we used earlier. Now in this case we don't have this n, this is the observed data. Okay, so observed data now is number of road accidents observed on last 5 days. So that we have written here 8, 12, 14, 7, 9. Okay. So 8, 12, 14, 7, 9. Okay. So this is our observed data last 5 days, and we assume that observation on ith day comes from a Poisson distribution with underlying parameter lambda such that where lambda comes from a gamma distribution with shape parameters a and b, where a is 10 and b is also 10. Okay. Now we can derive analytical posterior. So for case of gamma conjugate prior, we know that, so this is something you can derive yourself as well, or you can take a look at cases of conjugate prior. So for a gamma prior, the posterior would also be a gamma distribution with shape parameter a plus sum of these observed data points, b plus n, so just n. So number of data points. So how many data points you have? 5. Okay. So that's it. So that will be the posterior distribution. Okay. So let us draw some samples from this posterior distribution. It's a gamma distribution. Let me draw 40,000 samples from this. This would be A plus some obj and B plus 5. So this is how the posterior distribution of lambda looks like. Okay, so it's centered around 4, and the 95% probability mass is somewhere between 3 and 5. So let us calculate what is this 95% probability mass. So what range contains 95% probability mass? So you can use quantile function to calculate this. So how do I do this? Quantile post samples and then probability equals to C 0.025. So basically I'm leaving 2.5% probability mass on the left hand side and then 0.975. So basically 97.5% probability mass. So basically these line will mark 95% range. So I'm leaving 2.5% probability mass on the left hand side and then 2.5% probability mass on the right hand side. So the remaining middle area is the one that contains 95% probability mass. Okay. So when I calculate this quantile, I get this. So 2.5% is at 3.06, 97.5% is 5.06. So this is what makes my credible interval. So this interval between 3.06 and 5.06. So this particular interval 3.06 to 5.06 is called 95% credible interval. Okay. Now the interpretation of this 95% credible interval is very different from confidence interval. You might have heard about 95% confidence interval in frequentist inference. Okay. This credible interval is different from confidence interval. How? Credible interval tells you, so in this case, for example, it tells you that you can say with this much certainty, this degree of certainty, that you can say this with 95% certainty or 0.95. Let me just write it more precisely. You can say with this much degree of certainty, 0.95 degree of certainty, that true value of the parameter you can say this with 0.95 degree of certainty, the true value of the parameter lambda lies between 3.06 to 5.06. Okay, so between 3.06 and 5.06. This is what 95% credible interval means. It says that you can say with 0.95, so this much degree of certainty, that the true value of the parameter lambda lies between 3.06 and 5.06. So the claim is about true value of the parameter, because the posterior distribution you are getting, it's considering lambda is a random variable, the parameter is a random variable, we are getting some approximation of true distribution of lambda. So there is some underlying true distribution of lambda. So we are getting an approximate distribution of that, or we are getting an estimate of that using our data. Okay. So if you calculate this 95% range, what it means is that you can say with this much certainty, 0.95 certainty, that the true value of the parameter lies between 3.06 and 5.06. Also, this particular statement, why we are saying 0.95 degree of certainty rather than saying 95% probability, or let's say in 95% cases. So for example, you cannot say that in 95% cases true value would lie between this and this. That statement wouldn't make any sense for Bayesian inference, because that particular interpretation comes from frequentist interpretation. Okay? Bayesian interpretation of probability is this, that probability measure is basically when you say that certain event has this much probability, we are making a statement about degree of certainty of that event. that if I say that event E occurs with probability 0.7, that means in the Bayesian framework the interpretation would be that there is 0.7 degree of certainty, that is quite high degree of certainty, that this particular event would occur. Okay. So, in this case also 95% credible interval means that we have a high degree of certainty, this much 0.95 degree of certainty that the true value of parameter lambda lies between 3.06 and 5.06. Okay. This is very different from frequentist interpretation of probability and frequentist interpretation of of confidence interval. So, in frequentist interpretation, probability is viewed as relative frequency of occurrence of something. So, if I say that some event E occurs with probability 0.7, that means that if you, let us say, repeat the experiment 100 times, then this particular event E would occur 70 times. Okay. So, that is the frequentist interpretation, okay, approximately 70 times, right. So, in frequentist framework, probability can be viewed as relative frequency of occurrence of an event with respect to total number of experiments that you have done. Okay. So, what would 95% confidence interval mean? So, you also get 95% confidence interval in case of frequentist framework, right. So, confidence interval. 95% confidence interval means that if you repeat the experiment for, let us say, for say 1000 times, I am just giving an example. If you repeat the experiment for say 1000 times, or let us say 100 times, okay, that would be more interpretable. If you repeat the experiment for, let us say, 100 times, then the coefficient, whatever coefficient you have in question, or coefficient or parameter value, let us say parameter estimate, would lie between within that range A B. Okay. So, if I say that this particular interval A B is 95% confidence interval, that means if you repeat the experiment for say 100 times, then the parameter estimate would lie between A and B in 95 times. Okay. That is the interpretation of confidence interval. So, if I say that let us say you are doing a linear regression model and you find that the 95% confidence interval for your slope parameter, okay, so for main effect of something, let us say for your slope parameter is, let us say, between 10 and 30, let us say that is your 95% confidence interval. So, that means if you repeat the experiment for 100 times and calculate that parameter estimate, okay, then the parameter estimate would lie between A and B 95% times. So, basically 95 times. So, that is the interpretation of confidence interval. So, if you think about it, this is more like a statement about what would happen in the data if you repeat the experiment. But in Bayesian framework, data is considered to be known and fixed. So, you already have data. Data is what you have. So, you are not going to think about simulating that experiment and collecting more data. You are only going to think about uncertainty only in terms of parameter estimate. So, all the uncertainty is captured when you are trying to estimate the true distribution of parameter, because of the key difference that parameters are considered random variables in the Bayesian framework, right. So, we are only thinking about certainty in estimation of parameter. So, how much certainty we have in parameter estimate. So, we are making a statement about the true value of the parameter. Okay. So, the true value lies between 3.06 and 5.06, and we can say this with certain degree of certainty. Okay. So, that is the key difference. So, every time when you calculate a posterior distribution, you can calculate its 95% credible interval, which is basically 95% probability mass, for example, in this graph. Okay. So, basically roughly a range in which the true parameter value is likely to lie. Okay. And that is a very good summary statistic that you will be using a lot further for linear modeling. Okay. because by gauging this 95% confidence interval, you can make some loose inference that what might be happening based on this particular data. Okay. So let us now come back to our problem of Poisson likelihood. So where we are trying to model the number of road accidents. So this was our data. So this is our analytically derived posterior. Okay. Now let us go to implement this in MCMC. Rest everything I will keep the same. Of course, the prior had changed. So rather than beta, when I initialize the chain, I will draw samples from a gamma distribution. So R gamma. Okay. So 1, 10, 10. So these are the parameter estimates, right? Number of samples, current state of the chain, right? Then here, do we still want to generate from normal? Yes, that's fine. But you can change the lower bound and upper bound. So we want lambda to be greater than 0. Okay, so that is fine, but we do not want any upper bound. So earlier we had parameter theta in binomial case, which had a lower bound as well as upper bound. Now lambda has only lower bound. Okay. Now let us go and calculate likelihood and prior for the proposal as well as the current state of the chain. So because our likelihood is now Poisson, so we'll use dPoise, right? DPoise, and rather than doing sum of observations, I think now it would be better to just have observation here. So there is no such thing as sample size, and lambda is proposal theta. Okay, so this will give you 5 likelihood corresponding to each data point. So you need to take a product of all those 5, which will give you likelihood, joint likelihood. Similarly here, rather than beta, it's a gamma distribution now. So d gamma, proposal theta, and it's 10, 10. Okay. By the way, you can also write AB here, so which are hyper parameters of your prior distribution, right? So AB are shape parameters of your prior distribution. Now here, you again go. Basically, you can use the same statement, but for the current state of the chain. Not for proposal theta, but for the current state of the chain. And here it would be d gamma, current state, A, B. Okay. Now forward transition, backward transition would basically remain the same because you haven't changed any proposal density. Now we calculate Hastings ratio here. Okay, so that also remains the same. We calculate probability of acceptance using minimum of 1 and H. We draw acceptance criteria from a Bernoulli distribution, and then we accept or reject, and we move on, right? So this is the workflow, right? Now step size, I think it would make sense to have a relatively longer step size. So maybe we can start with 0.5 and see what happens, because the scale of lambda is quite high compared to theta. So lambda is varying between, for example, 3 and 5. So scale of lambda is going to be larger. Okay. So let us implement this. Okay. So upper bound is missing somewhere, I think in this distribution. So it requires some upper bound. So if you don't have an upper bound, you can just say infinite. So I'm going to run the entire code up to this, not this point, just up to this point. Okay. Now I can store basically this as df post right? And then I can visualize chains, right? Okay, so chain seems to be mixing well, right, at step size of 0.5, right? So you are able to recover the posterior between 3 and 5. Okay, so this seems fine. Now, if you want to compare it with analytical posterior, you can do that here. Oh, so what's wrong? So this was analytical posterior, and this is posterior using MCMC. Okay, so this is what is causing the problem. So I can write it from 1 to 7. Okay, so here this graph compares the analytical posterior and the MCMC posterior. So this looks really good. Posterior recovery looks really good with Markov chain Monte Carlo sampler. Okay. So the red one is analytically derived posterior and blue one is MCMC posterior. Okay. But I think it can still be made better. Let us check the rejection rate. So how much is the rejection rate with step size 0.5? So rejection rate is chain 1 reject divided by chain 1 reject plus an iter. So rejection rate is 28%. So it's good. Okay. So we are doing good. Now let us see what happens if step size is quite small. Let's say 0.01. Let's see what happens in this case. Rejection rate is very low, 1%. Okay. So that means there are a lot of correlated samples and your Markov chain are accepting most of the samples. That means chains are getting stuck somewhere. They're trying to move towards higher posterior density region, but they haven't reached there. Okay. So they are on a way to higher posterior density region. So that's why acceptance rate is too high. So let's see. So this is a comparison of two step sizes. So in this case, step size is 0.5. Chains are mixing really well. This is the case of step size 0.01. And you can say that chains are trying to reach towards higher posterior density region. They started somewhere here. In fact, all started close to each other, but they were getting stuck in different regions. So for example, it took, I don't know how many, almost 6,000 samples to reach this chain 1 at a value of 4.3 or something. Okay, so that's really bad. So okay, but for the other case with the step size 0.5, everything seems fine. You can also increase the step size and see what happens. By the way, if you run this thing again, you might see different initialization of the same chains, right? But the problem, I think, why the initialization looks at the same point is because of our prior. So our prior is such that chains initialize lower here, right? So let's say if I allow a prior to be, I don't know, let's say 50-10 or something. So maybe this will change things. Well, at least the initialization distribution is 50-10. So let's see what happens with this. And a step size of 0.005. Let's see. See, now the rejection rate is 0.7%. That's too low. Just bind it and let's draw the plots. Okay, now you can see. Now chains are initializing at the top part as well. So see, these ones are initializing here. So actually, if your step size is reasonably good and other things, given other things in consideration, you should see a behavior like this. So chains should mix well regardless of where they initialize, doesn't matter. So for example, even in this case, chains initialized at 0, but they quickly converged towards this high posterior density region. You can actually check that. What you can do is something like this. So you can draw the same plot again, but only for sample ID less than 300. Okay, or maybe less than 100 because they are converging very quickly. So now you will be able to see the behavior. So what happens in the initially? So when chains just started sampling, right? So see what happens is that, well, these chains are not doing much up to samples 100 because they're getting stuck. The step size is too low. But for this particular chain, you would see they started here and it took only 10-15 samples for these chains to reach here in high posterior density region, and then they almost started sampling from this region, and you would see that they would fluctuate a lot. Although for a very low sample size, it might look like that they are not mixing well, but you should see it in perspective, at least for 1,000 samples or so, to visibly make that case that whether they are mixing well or not. They are mixing well because they are fluctuating. All chains are fluctuating and in the same region, and they are on top of each other. All right, so this is the example using basically using a Poisson distribution where you are modeling the rate number of road accidents. What if you are interested in modeling something like, let's say, reaction time data from a task? Okay, so let's say you are doing some reaction time experiment. It could be, let's say, Simon task or Stroop task, or let's say word recognition task, and the reaction time that you observe in the task are somewhere around 256.6. Let me just write it as data here. So observed reaction times are, let's say, these are the reaction times you're observing. In fact, let me just generate it from RL norm distribution. So let's say these are the observed reaction times. We are observing 100 reaction times, or maybe, I don't know, 500. Okay, 500 reaction times from distribution 5.7 and 0.3. Okay, so these are the observed reaction times on a task. Oh, looks different. just write it like this. Okay, so this is how they look like, and this is how typical reaction times also look like. So there wouldn't be any observation, let's say below 50 millisecond or so, and the distribution is asymmetric and it would have long tails on the right hand side. Okay, so this is how, this is what the data is, right? Now you make the following assumptions, following model assumptions. So this is your likelihood assumption, okay, and then you will make some prior assumption. Okay, so likelihood assumption is this: you assume that reaction time in the ith trial comes from a log normal distribution with mean mu and let's say sigma parameter being and sigma parameter, right? So two parameter mu and sigma, it comes from a log normal distribution. And then you make some prior assumptions, and your prior assumptions are like this. So for parameter mu, you make a prior assumption that mu comes from a normal distribution with mean 6, standard deviation 0.5, and for sigma, you assume sigma is fixed. So let's say sigma is known for the simplicity of the problem, so we can deal with it later. Okay. So these are your model assumptions. Now your goal is to implement a Markov chain Monte Carlo sampler to calculate posterior distribution of mu given the data, so observations, and given the fixed value of sigma as well. So this is what you need to calculate. Okay, so you want to calculate posterior distribution of mu, okay, given these prior and likelihood assumptions. So how would you do this? Okay, so this is I'm giving you as a practice assignment. I will discuss this in the next lecture. Okay, so this is not very straightforward. This will be slightly difficult to implement using the existing MCMC algorithm we have, but you try to implement this and then think why this is not working. So think about the problem and try to solve it. Okay, also take a look at what would be analytical posterior for such a situation. Okay, oh, actually in this case it won't be analytical. If you would have normal likelihood, then you can derive analytically derived posterior, but in this case it's fine. So don't think about analytically derived posterior, but what you can do is you can calculate a posterior using grid approximation and a posterior using MCMC, and then you can compare them. Okay, so that's what we will try in the next lecture. So I will leave it here. In the next lecture, we will do this example using MCMC sampling, and we will discuss what problem can occur in example like this and how to solve this. So this will also become a good foundation for how these samplers work. Okay, so actually, as we go further in this course, you will not really need to write these samplers by hand. You do not need to write these algorithms, implement these algorithms in R. They are already ready-made packages. So for example, BRMS, STAN. So there are already some packages that will do sampling for you, that will do posterior estimation for you. You just need to specify your likelihood and prior assumptions, and everything will be done by those packages. But still, it is important to understand what is going on in the background, the consequence of a step size, in what situations model do not converge, how to figure out whether models converged or not, right? And what is the underlying working of these algorithms, right? So that you know all these things, right? And when algorithms can fail, how these are being resolved, what is exactly that these algorithms are computing in the background, right? So all this is important, right? So all right, so in the next lecture we will discuss the example using a log normal likelihood where you have 500 reaction time data points from an experiment. So this is more realistic setting. So you have reaction time data with 500 observations, and now you want to model it. So let us use MCMC sampler to calculate the posterior distribution. All right, thank you very much.